So in the last class, we had looked into some properties of sets and some operations that we can perform on sets. So in this class, we will look into in more details the properties of the operation on sets. So if we take examples of the operations that we discussed, so for example, if we take A to B, a set which is B to B, then obviously A union B is A intersection B is A minus B is B minus A is, and if we take U to B, then A complement is B complement is. This is some very basic example of how to find these quantities. Now, if we look into more details into the properties of these sets, then one of the first properties is intersection, and associative. That is A intersection B intersection C is same as A intersection B intersection C, and A union B union C is equal to A union B union C. And these properties are very easy to verify. That if we take the three sets like this, and if we take the union of the first two sets and then take the union with the third, is the same as saying taking the union of the last two sets and then taking the union with respect to the first. And similarly, with respect to the intersection, associative property holds. Similarly, this commutative property, which is also quite trivial, says that A intersection B is same as B intersection A, and A union B is same as B union. So all these properties are quite trivial. So we are not discussing how to derive at them. The first somewhat non-trivial property is the distribution of relationship of union and intersection. So if I try to perform A intersection B union C, this same as A intersection B union A intersection C. And if I want to do A union B intersection C, this same as A union B intersection A union C. And these sort of properties are what are called distributive properties. So many of these properties can be proven by what is called the Venn diagram. I mean, you can prove them by following the Brewster notation or the recursive notation, but one can figuratively also verify these properties which through what is called a Venn diagram. So if I have a universal set like this, and I can depict sets like this, then we can sort of shade the regions which we are trying to prove to be equal. So for example, if we want to look at this region which is an intersection B union C. So B union C and the intersection of with A is this region. And and if we look into this quantity, which is an intersection B union A intersection C, so if I want to look at this quantity, so and B intersection B is this quantity, and A intersection C is this quantity. So if I take the union of both of them, again I will get this quantity, this region which is already depicted here. So both these two regions are the same, and obviously one can verify these other distributive property, which is this one, also using Venn diagrams. So equality of sets, if you want to prove it more formally, the equality of, as we discussed, the equality of two sets can be proven. So if you want to prove that two sets A and A prime are same, you basically have to prove these two things. And if you don't want to prove these these identities without using Venn diagram, you have to show it in in a in this form. So let us look at this. Let us look at this identity, and I will try to prove it in the using the using this technique. So the identity is A union B intersection C, the same as A union B intersection A union C. So if I want to prove that both these sets are equal, I will call this X and this is X bar. Oh, sorry, I should not use the term X bar. So I will call it X1, X2. I have to prove that X1 is a subset of X2 and X2 is a subset of X1. So if I take any element A in X1, I have to show that A also belongs to X2. So A belongs to X1 means A belongs to A union B intersection C. That means A is in A or A is in B intersection C. The same as saying A is in A or A is in B and A is in C. And what is, so if I want to show that A also belongs to X2, I will have to show A belongs to A union B or A belongs to A union C. And the same as saying A is in A or A is in B and A is in A or A is in C. So basically you can see that if you if A is in A or A is in B and C, A is in C, then this is same as saying this. And these two predicates are basically equal, and hence these two sets are also equal. So basically what we have seen is that union is distributive over intersection and intersection is distributive over union. And these properties are basically called distributive properties. Now we will look into some properties involving complement. So one of the first few properties of complement is what is called the De Morgan's law. Uh, the, if you look at A complement, A union B complement, this is same as A complement intersection B complement. And if you do A intersection B complement, which is same as A complement union B complement. So as you can see that in De Morgan's law, the union and intersection get flipped. If I want to prove another De Morgan's law, which is complement of A complement is A again. Not really part of De Morgan's law, but yes, it is a property of the complement. So if I want to try to prove this result, so I will prove one using Venn diagram, another using maybe just notations. So if you have A union B and the complement of that, say union B is this region and the complement of this is this region. And if I look at this as A union B complement, if I want to look at A complement intersection B complement, so A complement is everything which is outside A, B complement is everything which is outside B, and their intersection is something exactly which is this region. So this is basically a Venn diagrammatic proof of the first, and the second is A intersection B complement A complement union B complement. So the intersection B complement means X is not in A intersection B. So X is not in A intersection B means X is not in A X is not in A. So how can you say that X does not belong to A intersection B? So there, so the way that X does is it may not belong to A intersection B is that X does not belong to A or X does not belong to B. Then only X will not belong to A intersection B, which implies X is in A bar or X is in B bar, the same as saying X is in A bar in B bar. So this is a notational proof of the second De Morgan's law. There are a few more properties of our section. There's a universal set SMT as a subset of U. Then S union is complement is U. And S intersection as complement is null. S is a subset of S bar is an ordinate. S is equal to 5. This is a subset of S bar. This is a subset of T. It can only E bar is a subset of N bar. So there are a few more of these properties which can be proven easily using Venn diagram or the notation. So basically the end of sets, and after this I will start with the topic of relations. Relations are also sets, but involving pairs of sets. So given arbitrary set E relation R this subset A cross A, or you can also write the set of A cross B if A and B are two distinct sets. For that, you have to understand the definition of X A cross B and the meaning. What is the meaning of A cross B? So A cross B is something a set of pairs such that the first element is in A and the second element is in B. So I have X as 1, 2, 3, and B as this and B as 3, 4. A cross B will be 1, 2, 3, 3, A plus A plus 1, 1 positive, positive, 1, 2, 3, 2, 3, 1, 3, 2, 3, 2. Because this that it is almost 4. Based on these definitions, we will further discuss the properties of relations.